Let us see how we can carry out this operation in the field. So, here as we had just now seen, we make use of a single loop of wire, right, is placed on the surface to induce as well as measure, right. So, here is a loop, right, which is inducing the radio frequency for some time, then we switch off the radio frequency, same coil now measures the signal, right. So, this helps in how we are able to achieve this, right. We are able to set up the alternating field through the surface loop, right. So, initially the protons are in equilibrium, now we are exciting them with the radio frequency, right. This excites the protons in the fluid below the subsurface, right. This NMR data is very sensitive to electrical and magnetic variations, right. The signal which we are measuring depend on some transmission cables, electrified railway network which may be 2-3 kilometers away from our site of investigation, but still all of them causes noise to the data which we measure, right. So, that is why I am saying the NMR data is sensitive, very sensitive to electrical as well as magnetic variations, right, and noise sources. Some of the noise sources are nearby railway line, nearby road or transmission line, high tension transmission line very close to our investigation, field investigation, all of them will cause some noise in the data. In order to get rid of this noise, we also use what is known as surface loop. We use some surface loops kept at different places, right, to overcome the noises created by such steel towers, transmission towers, right. These loops are used to receive the ambient noise, right. It tries to get the ambient noise, right, and this noise which we have measured, that means we do not use this NMR tool at all, right. We do not transmit the alternating magnetic field here, but we want to use 2 or 3 loops kept on the surface to capture what is the quantum of the field that is experienced by the loop, right. That means these reference loops are used to get what is the noise level. The same noise level will be applied to the field measured data. This process is known as noise cancelling. It is just like we many of us use noise cancelling headphones or earbuds. What does it do? So, apart from the speaker here over our ears, it also has got a sensor. That sensor continuously measures the ambient noise which our ear is able to get, right. So, accordingly it generates some pulses in the opposite direction. So, the noise created somewhere does not reaches our brain at all, because our headphone on the left ear continuously transmits some signal. That signal will nullify the noise which I get from the surroundings. That is what is the noise cancelling headphones. More or less in the same manner here, we sensed what is the noise that exists over there due to several reasons. As I told you, mostly due to man-made objects, transmission lines, metal fence lines, right, railway line adjacent to our measurement point, or transmission towers as you see in this image, right. I am circling. All of them will cause some noise. This noise is picked up initially by keeping some receiver coils. right? We get the receiver coils signals, right? Both are done simultaneously, right? Here we carry out the survey by transmitter and receiving. Simultaneously at the same time we are also using some receivers. So, at the same time we have the total signal as well as the noise alone. So, what do we mean by noise? Noise is obtained without we generate any radio frequency, right. Since we have both, we will be able to correct the data which we have observed using the NMR instrument, right. So, how? Because making use of two reference loops, we know the noise level, that is we know the background level. So, that will be subtracted from the data which we will get from the field investigation, right. This is the noise cancellation part. Now, what we have seen, so we use a single loop, right, that is capable of inducing as well as receiving, right. Since the protons are obviously will be aligned according to the Earth's magnetic field, now we are going to turn off the alternating magnetic field which we are creating. Now, after turning off, we are receiving the signal in the same loop. We have seen already, seen in the same loop. So, this is what is happening, right. So, what happens, this beneath this is the ground surface, below the ground surface we have fluid, mostly here in this case it is water, and the magnetic moments of this water will be aligned parallel to the Earth's magnetic field. So, they are all aligned as you can see here, right. So, they are all aligned parallel to the main Earth's magnetic field. Under such a situation, we lay our transmitting cable, right. As here you can see, it is more or less in a circular form. This transmitter cable is kept on the surface of the Earth, and using this cable we excite the protons. So, upon excitement, you look at the orientation of the protons. So, initially in this picture number 1, they were aligned like this. In picture number 2, their direction has changed to 90 degrees from here, right. So, this is the transmission space, this is equilibrium phase, this is excitement or transmission. Now, we switch off the transmission, and now as soon as we switch off, these protons which are aligned like this now turn back to the original position, as you can see here, right. So, this spinning causes some signals which are received by the receiver of the nuclear magnetic resonance. So, this is how we carry out the work in the field. So, the survey can be carried out in all the dimensions, either 1D, 2D or 3-dimensional, something similar to the electrical resistivity survey, right. So, here 1D data set can be obtained. This is usually referred as MRS, magnetic resonance sounding. We use more or less similar words there to vertical electrical sounding. In vertical electrical sounding, what did we do? We progressively moved the electrodes so that the depth of current keep on increasing over a common center point. So, here too we will carry out the survey by keeping the transmitter at the same location, but we will vary the current so that depth of penetration is increased. So, this survey is known as 1D survey, which is known as magnetic resonance sounding, right. Instead of 1D, we can also do 2D survey. So, how can we do 2D? So, initially transmitter coil is kept like this and we completed one survey. Then the transmitter coil is shifted. Okay. This is the second location. Then this is the third. So, this is how transmitter coil is keep on being moved along a particular profile. So, this is known as 2D magnetic resonance sounding. So, we had here you can see a blue colored rectangle, initially it was like that, then we shift it here take sequence of measurements. This is how we keep on shifting the loop on the surface, thereby we will scan one profile, that means one section we are able to scan. So, this is known as tomogram, right, same word we used also in electrical resistivity survey. So, 2D profiling is referred as magnetic resonance tomography, right. What it does is, which uses overlapping locations of loops as I have drawn here, right. Then now we have information along a profile. Same thing can be done for the next profile as I am drawing, right. This helps us to come out with the 3D configuration of the subsurface, right. Since we have magnetic resonance tomogram at different sections, we can interpret the formation between the two. Hence, this method from 2D it can be made to 3D also, right. So, we will be able to arrive at the 3D subsurface model using NMR technique, right. So, what we are going to do is, in order to vary the depth of measurement, right, measurement depth is changed. How we are able to change? By applying different sequences, different pulse sequences that focuses the pulse moments at a specific depth range. That means, the alternating magnetic field which we are going to create by laying a loop on the surface, right, that helps us to understand the magnetic moments of the protons in the fluid, right. How we are able to focus our attention to different depths beneath the surface? We are able to do that because depth of investigation using NMR technique is equivalent to transmitted strength signal multiplied by the duration of the signal, right. In NMR, we do the survey multiple times by transmission stopping, transmission also done on different current level. So, signal strength also is varied. So, signal strength is progressively varied, right. And similarly, signal duration for which we are going to excite the subsurface can also be varied. So, we have duration in our hand, signal strength in our hand. So, we can play with this to understand the conditions at different depths below the surface of the earth. How? Because depth of investigation is dependent on the signal strength as well as the signal duration, right. So, since we are by varying the transmitted signal strength as well as the duration, we are able to scan different depths of the subsurface, right. So, we are able to carry out the survey with various Q values. What is Q? Q is nothing but signal strength multiplied by the signal duration, right. By playing with that, here is an example available in this agency, which is the German Geological Survey. Here you can see the first case, right, where there is a layer A present at a depth of 10 meter below the surface of the earth. The same A layer is sensed by the NMR, this dotted line, right. So, this is A, right. So, here this layer is at a depth of only 10 meters. So, here you can see we get maximum signal here, right, the dotted line. So, signal amplitude was very high. What does it indicate? Because within 10 meter you have a porous formation, the blues are water bearing formations, due to which you get very high signal, right. In the case of B, right, in the case of the second diagram, this diagram, here you can see, since the permeable formation or water bearing formation is at a depth of 50 to 100 meters, 50 to 70 meters, initially the signal amplitude is less, only in this zone it is the maximum, right. So, that means at some depth you have a permeable formation. So, this is how by varying the signal strength of transmission as well as duration, we are able to focus and understand different depths below the surface of the earth, right. So, we have seen formation A is within 10 meters, here formation B is at a depth of 50 meters. If you have something like that, you end up in getting a signal falling along this line. Suppose both A and B are present, then you get a combination of this as well as this, which is indicated by this solid line, right, which is A and B. So, this is how by varying the signal strength as well as by varying the duration of the signal, we take multiple images at the same surface, right. In this help us to understand the locations or formation at what depth is having water, we are able to answer by carrying out the nuclear magnetic resonance survey. As we were discussing, size of the loop, right, and shape, right, circular ones or rectangular ones, right, or 8 shaped one loops, we can arrange in different manner. So, the idea is we should have minimum noise, right. So, size of the loop as well as the shape and distance affect the amplitude of electromagnetic field we are going to receive, right. So, here you can see, so this is what is happening. So, first is the excitation phase. So, when they are excited, that means we are sending in some alternating current through the loop, which makes, so this is the signal intensity, right, excitation intensity. At this time we are going to stop the current. So, this axis is the time axis, right. So, we were exciting the protons below the surface until this time. So, at this time we stopped the application of the current, radio frequency. After the application is stopped, what happens? The protons are now aligned parallel to B naught. So, this is the alignment of proton also. After we stopped the current, it slowly starts spinning and reaches the original position. So, during this process, right, it initially you do not have any signal, but after some time it starts moving, right. So, this is the initial amplitude, this is the amplitude subsequently slowly spins and reaches its original state. It now completely get relaxed. This time is known as decay time T, right. So, here the loop we have laid on the surface is transmitting. Now, we switched off, the same loop is now recording or receiving the signal. So, this is how the survey is carried out in the field, right. Now, let us look into some interesting results. So, here is the synthetic results, but it is quite interesting. So, response of surface nuclear magnetic resonance, it is a calculated or a synthetic response, right, for water layers at different depths, 10 meter depth, then 5 meter depth, 1 meter depth, right. These are all water bearing formation, and they have also considered different thicknesses. This is the depth, right. Then what is the thickness of the formation? Thickness of the formation are varied from 1 to 5, right, for 1 meter layer. This is how they varied. So, here you can see they were considered at different depths and with different thicknesses of 1 meter, 5 meter and 10 meters, right. So, 1 for 1 meter, 2 for 5 meter, 3 for 10 meter. So, here itself I can write. So, here is the thickness, it is 3 meters for 10 meters, for 5 it is 2, for 1 it was 1 meter, right. What will be the response? So, if you look at the first one, that is 1, right. So, we have assumed a layer which is leading to an amplitude of this much, right. So, these are the 3 layers, first one layer 1, layer 2, layer 3. Please see their peak gets kind of offset, that is controlled by what? That is controlled by the thickness of the formation as well as its location from the ground surface. So, 1, 2, 3 here refers to the different formations which are located at 1 meter depth, 5 meter depth and 10 meter depth, right. Now, let us look at these dashed lines 1, 2, 3. What does it indicate? They indicate, right, the thicknesses of formations have varied, right. So, their thicknesses are varied, then they are little bit, their peak got little bit reduced, right. Then the third case, very much it got reduced. So, this is 1, quickly you are able to see the peak, that means the first layer, right. This is the second layer, then this is the third one, it is at a 10 meter, right. At 10 meter depth you have a 3 meter thick formation. So, this is how this diagram clearly help us to understand how the location of the water bearing formation from the ground surface as well as its thickness control the SMR signal. That is what we have seen in the previous slide, in this slide. Now, let us also have a look into how the SMR signal help us to understand about the grain size, right. So, here you can very clearly see this is the scale indicating the grain size, right. With reference to the grain size, if you look at the NMR decay time which is shown here. So, decay time is very less for which one? Very fine grained formation. Why it is very less? Already when the formation is made up of very fine grains, the size of the pores are so small, right. So, over there the magnetic moments, right, or the protons they precise or they very quickly spin and reach the original position, original state. That means they quickly relax, relaxation time is very less in the fine grain. Whereas, if you look at the coarse grained formation which is of about 10 millimeter in size, right, about 1 centimeter in size, such gravel deposits, their pore size is so huge, you have large volume of water, right. That means, if you see one void, that void will have maybe of about half a centimeter in size approximately. It is now occupied by water, so many protons are there. So, it takes more time to relax. So, this is the relationship between the grain size and the NMR signal. Once if you are able to understand the grain size distribution, grain size can also be related to the permeability. So, here is the grain size versus permeability. These two relations are more or less identical, right. When the size of the grains are small, as you see here, right, both of them are more or less similar, right. When the grain size is smaller, NMR signal is less. Similarly, permeability is less. Permeability is the ability of formation to transmit a fluid, right. And next is somewhat better. When the size of the grains is about 1 centimeter, then you have very high permeability. Right. Similarly, let us now focus our attention on water content. Water content in the saturated zone is the same of porosity. It is the same as that of porosity. Right. So, here is the grain size distribution. This is the total porosity. Right. And here we have effective porosity as well as adhesive water. Adhesive water and freely moving water can be distinguished using SNMR, we have seen, right. So, we are able to segregate that too. So, here with the help of SNMR, we are able to arrive at the total porosity as well as the effective and adhesive porosity. This is another application of SNMR signal. In this case study, they try to understand how the water content beneath the surface, that is groundwater content, is varying, right. This researcher has carried out about 4 or 5 soundings on the surface, right, which these locations were 25 meters apart using a 8-shaped loop antennas with about 50-meter diameter. So, very large transmitter coil were used. So, they describe they had gone ahead for 8-shaped because there were a lot of noise they were receiving at that site because of a electrical railway line, right, a railway line which is an electrified railway line which was at a distance of about 4 or 5 kilometers, even that has led to some noise. To reduce the noise, instead of using a standard typical rectangular or square shaped or circle shaped coil, he has used 8-shaped antenna, right. From these 4 sides, the results are given here. One is the top one is water content, right. The next one is the decay time, right. These are all the measured amplitudes, measured amplitude and measured decay time, right. These are all the measured values. So, B is the actual measurements and A is the inversion. So, we have been seeing about inverse models almost in all geophysical methods. Here too, what is inverse model? I have mentioned many times. So, here is the raw data. In order to get a data something like this, what is likely to be the conditions of the subsurface? So, we assume some geological configuration below the surface and calculate the SNMR signal, right. NMR signal is calculated, we compare with our observed values, not matching, rework. So, this process is continued and then we arrive at the inverse model. So, using the inverse model, we are able to understand at different depths. So, this is the depth axis. At different depths, what is the content of water? No other geophysical method can give such a nice information, right. So, this is how we are able to understand how water is distributed below the surface of the earth using the nuclear magnetic resonance technique, right. To add up to this, as I told, as we had seen just now, inversion also help us to get some surface images. So, this is the measured data, right, and this is the modeled data, right. So, here you are converting the time in terms of depth, right, in terms of depth versus relaxation time, right. So, here is the pulse moments versus the measurement time. The measurement time is converted into depth. That means, so we had focused our current, the current was going down and down as we increase the strength as well as the duration. With the help of that, and then by inverse model, we are able to arrive at the subsurface cross section, right, by inversion. What the map we are able to get? We are able to get the water distribution beneath the surface. So, here is the legend. So, how much of water is present below the surface, right. So, these are the zones where there is more presence of water content, right. So, here is this has been transferred in terms of water distribution. So, this is the depth and how the water was distributed below the surface. So, maximum water was present in this zone, and this is also compared with the lithology, right. So, these are all some of the potential advantage of surface nuclear magnetic resonance imaging. To conclude, the broad applications of SNMR are, we had seen repeatedly, I was also telling, to understand the water content both in the Vadose zone and in the saturated zone, where water content refers to porosity. Number 2, it helps us to also understand hydraulic conductivity. How? Using some empirical relationship. Please remember, NMR does not directly measure the hydraulic conductivity, it measures only the water content. Using that, we can, using empirical relation, we can determine the hydraulic conductivity. So, once if you are able to have the value of porosity and K value, that help us to understand about the aquifer conditions. When the porosity is reasonable, when the formation is made up of sand, obviously hydraulic conductivity will be more. This is how we are able to characterize the aquifer system. We are able to understand about the Vadose zone, because if this is the ground surface, if this is the water table, right, groundwater table, right, the moisture content in this zone can be estimated using the SNMR. So, it helps us to understand about the Vadose zone. Suppose if we are conducting some experiments, maybe a percolation pond, how the water is migrating below the surface can also be continuously sensed by SNMR. Also, this method is used to understand the variation in soil moisture below the surface, right, and it helps us to arrive at some constraining parameters, right. For example, hydraulic conductivity. For this aquifer, we can use an hydraulic conductivity of 75 to 150 meter per day. Like that, we will be able to arrive at some range of parameters, because we are able to estimate the porosity. From porosity, empirically we can arrive at the hydraulic conductivity, which can be used in groundwater models. For groundwater modeling, we can derive the parameters using nuclear magnetic resonance imaging. Also very much used in contamination studies. For example, if the aquifers are getting contaminated with oil, we will be able to identify zones that are affected by oil contamination using the SNMR. And in such zones, if we are going in for remediation, right, how effectively we are remediating the region can also be assessed by, that is what is environmental remediation, can also be assisted by repeated SNMR measurements. In geotechnical assessments, porosity very much helps us. Formation with very high porosity are likely to be very fine grain. So, presence of clays, which are a hindrance for major constructions, can be deciphered very nicely using SNMR techniques. These are all the broad applications of SNMR. So, today we had looked into this very recent tool of nuclear magnetic resonance, how the nuclear magnetic resonance imaging that has been used in health industry or in hospitals or in health services, they are in use for longer period of time. The same technology is also used to understand the subsurface. This is what we have seen today. It helps us to directly detect the presence of water as well as fluid that contains protons, especially hydrogen. And toward the end, we have seen this list of applications of SNMR methods. Thank you very much.